We're going to be looking at reaction mechanisms in this video. So what is a reaction mechanism? It's the sequence of events that describe the actual process by which reactants become products. It's called a reaction mechanism. So this is the kind of stuff we are going to look at. Here's our overall equation, here's a rate equation, and here are some elementary steps. We'll get into that in a little bit here. Before we do, reactions may occur all at once or through several discrete steps. Each of these steps is known as an elementary step. So if you have a balanced equation and you have a whole bunch of steps that sort of reduce down to make this balanced equation, like canceling out and things like that, like finding things that are in common, canceling. Anyway, these are the elementary steps. So in a multi-step process, one of the steps will be slower than the others. The overall reaction cannot occur faster than the slowest step, which is known as the rate determining step. So we have two scenarios here. We have cars getting slowed at Plaza A and Plaza B, and then again getting slowed at Plaza A and Plaza B. And I can't really figure out what this means. I think it just means that we have this is our rate determining step for that one, and then this would be our rate determining step for that. I don't think they have any connection, the two. I just thought it was a nice picture. So we have two steps that we have to follow, or two requirements. The first one is the sum of the elementary steps must give us the overall balanced equation. We just have to double check that. And the mechanism must agree with the experimentally determined rate law. Now we're not going to actually look at any experimental data. We're actually going to be able to come up with the rate law based on one of the elementary steps, and that's something that we'll come to here. Let's take a look at an example. Given the proposed mechanism for the reaction, so here's our two steps. I want us to rate the overall reaction. So here are the two just put again, just wanted to rewrite them. And there's our line. So all we need to do is we need to cancel out things that are occurring on both sides of our equations. So I see an NO3 here, and I see an NO3 there. Those go. We've got two NO2s here, and we have another one here. So let's cancel one there and one there. So we should have left for our overall. Those are going to be our two reactants, and those are going to be our two products in any particular order. So there is your overall reaction for this one. Next, I want to identify the reaction intermediates. Now, what are these? These are the entities that are neither reactants or products, but they're formed and consumed during the reaction. So essentially, they're the things that cancel out. So here are our two steps, and I guess I just did sort of cancel some stuff out. However, the only one that cancels out is both a reactant and a product is this NO3. Okay, those go. Sure, we did cancel out an NO2, but we actually still had one left over. So the NO3 is our only reaction intermediate in this particular reaction. Moving on, identify the rate determining step. And to do this, all we're doing is we're looking for our slowest step. So this should be pretty obvious. So listed there are the slow and the fast. So, I mean, that says slow. That's going to be our rate determining step. There it is. Yeah. Okay, now we can actually tie what we learned last section into this. So we want to write the rate law equation for this reaction. So how this actually works is we actually need to just sort of look at our slowest step, because this is determining how things are produced. And all we need to look at is we need to look at the entities, 1, 2, 3 entities, and the reactants of our slowest step. So there they are, and there's actually two of them. So what we actually can do here is quite a nice little cheat step. So that's our slowest step, and I just simplified it a little bit. So instead of writing the two separate ones, I wrote it as a 2 there. And then all we're going to do is we're going to take our reactant and put it there, and of course we have our constant, and this exponent is actually the coefficient here. So we learned in our last lesson that the coefficients cannot play into determining the rate law. However, they do in the slowest step here. So you can't look at your overall equation and come up with a rate law exponent. All you can do is look at your slowest step, and then any coefficients will become the exponents. I think that is quite a nice little shortcut. This table here essentially just describes what we're talking about here. So if you have one product, you'll notice we've got a rate law and an exponent of 1. This is exactly what we just had in the last one, and there were 2 of them, so we had a 2. Sometimes you've got multiple things, A, B, so you've got each with a power of 1. Here we've got 3 A's, and so we get an exponent of 3. A couple of A's and a B, squared and a 1, and an A, B, C, and then those are all to the first exponent. So there you go. That's a nice little shortcut for determining the rate law. Okay, so for this example, first we'll start by writing our overall reaction. So given our proposed mechanism, there we go. What we're going to have to do is cancel out some things. So firstly, I'm looking and I see some a lone Cl and a lone Cl, gone. A ClO and a ClO, gone. And not that these equations line up, but they have an O as a reactant and an O as a product, so we've done it. So here's what we've got. We've got a couple of O3s, and we have 3 O2s. So that should be our overall, and there it is. So there's our overall reaction. Again, we cannot take our reaction mechanism from this overall. Does not work out. It's going to come from one of our steps. Next, let's identify the reaction intermediates. So that was all that stuff I just canceled out. So it was the Cl's that canceled, the ClO's that canceled, and the O's. There weren't any charges on any of these things, but there we go. And those are your reaction intermediates. Nextly, we'll do this one a little backwards. So what I'm going to give you is I'm going to actually give you the rate law, and I'm going to say, determine which is the slowest step. So what we need is we need one of our steps that only has O3 in it. So I guess right off the bat we can eliminate step number 3 because it doesn't have any O3s as reactants. So that's gone. Step 2 just has O3, and step 1 has Cl and O3. So it's got a Cl. So we can't have this thing here. So it can't be 2. So it's got to be, sorry, it can't be 1. So it has to be step 2. In terms of our, yeah, so there we go. So this matches this. Our exponent is 1 and 1, right? 1 and 1. So we've determined that step 2 is the slowest. There we go. That's your slow step. So if you knew that, you could go right to the rate law. And so those two are fast. So you can also have a catalyst. So catalyst speeds up a reaction without being consumed. And for this reaction, there is a catalyst. Now the one catalyst, to fit the definition, it has to start as one of your reactants and finish as one of your products. And so Cl actually is our catalyst in this reaction. Now, you might be thinking, well, what about the ClO? Well, it's actually, it ends up the first appearance as a product, so that doesn't work. It's sort of backwards. It's not really a backwards catalyst. It's just not correct. Again, we are after something that starts as a reactant and then is kicked out as a product. Even though it does sort of cancel out in the overall things, that doesn't really play into this step. So I want to take a look at one last problem here. So here is our reaction, and it's asking us to sort of confirm our rate law, and it gives us our elementary steps here, and all we want to do is just sort of confirm this thing. So I think this one looks probably pretty straightforward. We've got our slow step here, so that's going to determine our rate law. So let's see, we have that thing right there with the exponent of 2, coefficient of 2 becomes the exponent of 2, so that checks out, and we also have an H, and so that's fine. So I suppose the only other thing we really need to do here is we need to just make sure that everything cancels, and that's exactly what happens. So would we consider this one to be reasonable? Well, it met our 2 requirements. Everything canceled out, so that was like our first requirement, and then the second requirement is all this stuff right here, and that seems to check out.